Hi everyone, welcome back to my channel. Now, these videos have been designed to take you through revision step by step on various topics that are included in your GCSE examinations. Now, we're going to start off by looking at an overview of the topic rivers and flooding. So that includes river features, river formations and landscapes, as well as river management and then flooding. So this particular topic is very popular in many GCSE specifications: AQA, OCR, EDEXCEL, WJEC and EDUQAS. So if you are going to be watching these videos, I advise you to have an A3 piece of paper with you, and as you follow me through this video, I am going to be producing an A3 summary sheet for revision to summarise the entire topic of rivers and flooding. So it would be a great idea if you could grab some different coloured pens as well as an A3 piece of paper. Now, my particular students, they study EDUQAS Specification B. You might study a different GCSE specification, but rivers and river management, river landscapes and flooding features very similarly in every single specification. So I'm going to provide you with an overview of this topic like I said before. So I'm going to go ahead and I'm going to put the title in relation to my specific GCSE specification. So that's EDUQAS Specification B. And I'm going to just make sure that title is nice and clear so that I know that this revision sheet is associated with river landscapes and river management. So we're going to start off, in that top left-hand corner of the A3 piece of paper. And I'm going to zoom in on the video so that it's nice and clear and it's easy for you to follow along as we draw diagrams, list keywords, and complete our A3 summary revision. Now, we're going to start off looking at the hydrological cycle. Now, the hydrological cycle is the circulation of water around the world between stores by various transfers. The global hydrological cycle is powered by solar energy. It is what we call a closed system in continual circulation. And this means that no water ever leaves the system or is added to it, with 99% of the water stored within the cycle, leaving only 1% within the circulation at any given time. Now, most of the water is stored within the world's oceans, about 97%. So I'm going to go ahead and I'm going to draw my body of water, my sea and my ocean, and I'm going to draw my sun as a representation that is powered by solar energy and heat energy from the sun. Now, when this heat energy or solar radiation from the sun hits and heats up bodies of water like a sea and an ocean, we will get that liquid turning into a gas known as water vapour. And this is through the process of evaporation. And evaporation then means that that water vapour is going to rise in the atmosphere, it's going to cool and condense, and it's going to form clouds. Now, evaporation takes place over large bodies of water, rivers, seas, oceans. So on the left-hand side of the diagram, I'm now going to add in some vegetation to represent grass, plants and trees. And that is because water can actually sit on the leaves of vegetation. And when this solar energy from the sun heats up this water, the water will evaporate off the leaves of the vegetation. And we call this process transpiration. When it then turns into this water vapour, it will cool and condense in the atmosphere again, and it will form clouds through the process of condensation. Now, when we have so much water vapour joining together high in the atmosphere to create these clouds, eventually we will get precipitation. Precipitation referring to water vapour that actually travels from the atmosphere to the ground in the form of hail, rain, sleet or snow. Now, when precipitation takes place, it can obviously hit various land surfaces. If it was to hit what we call an impermeable surface, this surface will not allow the water to penetrate and soak in, and it will encourage a process known as surface runoff. However, if we get precipitation on permeable surfaces such as soil, grass or clay, that water will be absorbed into the soil and into the grass, and we call this process infiltration. when infiltration takes place, we then get that movement of that water running through the ground surface, and we call this percolation. As those water droplets and particles move through the ground through percolation, it will eventually hit groundwater, water that flows through saturated rock or soil deep below the ground surface. And then it will lead back to a large body of water known as through flow. Don't forget as well, trees also provide interception. So they restrict and stop precipitation, hitting the ground surface, and it is collected on the leaves of the vegetation. Now, when it comes to the hydrological cycle, we have two key words we also need to know. And that refers to the various stages of the hydrological cycle being categorised. So the first is stores. And a store is where water remains in one place and state in a given time. So that could be a solid, liquid, or a gas. So I'm going to go ahead and I'm now going to add in my key geographical words in relation to the hydrological cycle, and I'm going to colour code them in terms of pink to represent our stores. So we've got our sea, our ocean, our trees, our plants, our clouds, our soil, our rock, and our groundwater. Now our second category is known as flows. And flows in relation to the hydrological cycle talk about the transfer of water between stores, either in the same state, a solid, a liquid, and a gas, or it involves a change in states from a solid to a liquid. So for example, on the diagram, you can see me adding the process of evaporation in a purple pen, because that is a flow. The solar energy from the sun heats up those bodies of water, it turns from a liquid into a gas, and it flows from the sea and ocean up to the atmosphere to form a cloud. Then we've got other processes like condensation, precipitation, transpiration, surface runoff when it hits the ground surface and the ground is impermeable and it won't let the water soak in, so it runs over the land and runs into the sea, the ocean, or a river. We've got infiltration, where the water is absorbed into the ground surface because it's permeable. We've got percolation as it moves through all that sand and sediment and soil deep below the ground surface. And then we've got the process of through flow as well. Now, that concludes our diagram for the hydrological cycle. So we're now going to start to think about how human activity can affect the hydrological cycle. So, different countries use different amounts of water, but we all tend to use it in very similar ways. Some of these human activities can impact the hydrological cycle positively or negatively, such as generating hydroelectricity, irrigating farmland, deforestation, and climate change. So we're going to go ahead and bullet point some of the human activities that can influence the hydrological cycle. So I'm going to start with some of the negative ones. So if we think about climate change, a big concern right now in the 21st century, that can lead to extreme weather events, such as storms and droughts. So if we have a drought, we've got limited amounts of water on the surface of the ground, and that will then limit evaporation taking place. On the other hand, if we have heavy intense storms, that's going to encourage precipitation, and that might lead to increased surface runoff and more water in your river, which is known as discharge. Now, urban development can also introduce impermeable surfaces like concrete and tarmac into a natural environment. And that means, again, it can increase surface runoff, meaning more water gets to the river a lot faster, increasing the risk of flooding. We've got dam construction, where we build structures across the river channel which impede the flow of water from source to mouth. We've got over-abstraction, where we as humans are taking out too much water from lakes, rivers and reservoirs and causing lower water levels. Deforestation removes trees from the natural area, which provide interception and prevents water travelling to your river a lot faster. But on the other hand, we've got some positives. So we've got afforestation, planting trees, which allows those trees to store water, limiting the amount of water that leads to our rivers and reduces the risk of flooding. You've also got conservation and restoration efforts where we are trying to maintain natural habitats and allowing them to store water so that we can still have processes like evaporation and condensation taking place. So now let's move on to looking at a river drainage basin. So a drainage basin is an area of land drained by a river and its tributaries, its small streams. A drainage basin is an example of what we call an open system because it is open to inputs from outside, such as precipitation, and it is also responsible for outputs out of the system, such as when water leaves the river and travels into the sea. The drainage basin consists of a number of features. So we're going to go ahead and draw a very nice diagram of a drainage basin and we're going to label those features. So in the upper course of your river, we have our source, the start of your river in your upland mountainous areas. Your small streams in your upper course are known as tributaries or a single tributary. When these two rivers join, we have this known as a confluence. And then as that water travels through your upper course down towards your middle course and then your lower course, we would call that your main river channel where the water flows. Now, rivers then lead to the ocean or the sea, and we call that the mouth of the river, the end of the river. Now, we can have two rivers very close by to each other in a similar location. So we can draw a dotted line around our drainage basin, and that dotted line is what we call the watershed. It's the boundary between two river drainage basins. Any water that falls within this drainage basin, inside those dotted lines, inside the watershed, that will then travel into this river and drain out towards the mouth at the end of the river. But any water that lands outside of the watershed will drain into another river, and that's what a drainage basin is. So I now want to touch on something called annual river regimes. So a river regime describes the annual variation, or what we call seasonal variation, in the discharge of a river. Discharge meaning the amount of water in the river at a given point in time. Now, rivers can have distinct patterns of discharge depending on a range of factors. So I'm going to share with you 3 separate locations. And I'm going to draw small graphs for each of these locations. So I'm going to have on my x-axis the months of the year, and what would be on the y-axis would be the discharge, the amount of water. Now, if we take, for example, a river in England, rivers in England could be surrounded by vegetation and have very large amounts of deep soil. The rock underneath is then potentially permeable surface such as chalk, so the river levels in England may remain relatively constant all the way through the year. However, if we then looked at an alpine river that runs through a mountainous region, we potentially will then have a drainage basin that contains glaciers. And it will also experience snow on the top of these mountains, which then feed into the river. So the snow falls in the winter, but then melts due to warmer temperatures in the summer. And this is then reflected in the discharge of the river rising in the spring and summer months, but then decreasing in the winter months. On the other hand, if we think of a river located in the Sahara Desert, we're going to experience a climate which is very dry. And as most of the river drainage basin is desert, the river will have relatively low levels of discharge, or it will be non-existent. In the Sahara Desert, it only rains occasionally, but when it does, it pours for a very short period of time. And this can cause flash flooding and a temporary rise in river levels very rapidly in terms of the discharge. And that's why that last graph is very, very flash, floody and spiky. Now, we're going to now move on to rivers. And before we look at river landscapes, we need to get familiar with what we call fluvial processes or river processes. So, there are 4 main processes that occur in a river which influence its shape. And these are erosion, transportation, deposition, and weathering. And all of these depend on the amount of energy that is in the river. So if we start with erosion processes first, erosion meaning the wearing away of the land. So the first erosion process is known as hydraulic action. And this is where we have water crashing against the river channel sides, and it compresses the air in the cracks and it expands those cracks and eventually erodes the river channel. Abrasion, on the other hand, is when we have eroded particles in the water, scraping and rubbing against the rock, removing smaller pieces. Whereas attrition is eroded particles in the water, smashing into each other and breaking into smaller fragments and rounding off their edges. Whereas solution is that weak carbonic acid in the water of the river itself, dissolving rock. Now, rivers are very special. They also have two additional erosion processes. And the first is known as vertical erosion, that V shape on the left-hand side, and that means downwards erosion, vertical erosion. Whereas lateral erosion on the right-hand side means sideways erosion. So we get more vertical erosion in the upper course and more lateral erosion in your lower course. So now if we concern ourselves with transportation. Transportation meaning the movement of sediment from one place to another. And there are four main types of transportation. These are traction, concerning large boulders and sediment being pushed along the riverbed. We've got saltation, where smaller particles like pebbles bounce along the riverbed up, down, and are carried further along the course of the river. Suspension is when you have your very fine particles like sand actually floating in suspension, suspended in the river channel. And then you've got solution, where particles are actually dissolved in the water and they are carried downstream within the water itself. Now, when the river loses its energy, it will deposit any material it is transporting. So deposition is another fluvial process you need to become familiar with. We've also then got the term weathering. And weathering means the breakdown of rock. Okay, so there are three main types of weathering: chemical, mechanical, and also biological. And biological weathering involves vegetation, plants, and their roots. So a river changes its shape as it flows from its source to its mouth. And this can be seen in a river's long and cross profile, which is what we're about to draw. So we're going to draw a small graph. And on the x-axis of that graph, we're going to have your distance from your source to your mouth. And then on the y-axis, we're going to have the height in meters above sea level. Now, we're first going to look at a river long profile. And a long profile of a river is a way of displaying the channel, slope, or gradient of a river along its entire length. And it shows us that a river loses height with increasing distance towards the sea. Whereas the diagrams I'm drawing now are cross profiles. If we were to stand in the middle of the river and actually slice across it from the riverbank to the other side. Now, a river cross profile shows us a cross section taken sideways of a river's channel and or valley at certain points along the river's course. There are three main sections along the long profile of a river, and these are your upper, middle and lower course, and each of them have their own channel cross profile features. In the upper course, the valley cross profile is very narrow and steep sided. Very much a V-shape cross profile is typical in this particular area of the river. This is because of vertical erosion, as well as hydraulic action and abrasion taking place. Whereas in the middle course, the river is flowing through lower lying land. It has a much gentler gradient and it encourages more lateral erosion. So it erodes the valley sides, making the channel wider. Whereas in the lower course, the river is passing through very low lying land, and this is where we have increased amounts of lateral erosion. But we also have flooding resulting in deposition building up the floodplain. And this is what makes the wider river valley in the lower course. Now, we need to concern ourselves with how the river changes from the source to its mouth. And this is known as the Bradshaw model. a theoretical model that helps describe the changes we would expect as a river travels from its source regions in the upper course with increasing distance downstream towards its mouth. So if we look at the gradient of the river and consider again the long profile, we notice that the gradient, the angle of the river, actually decreases, whereas the discharge, the amount of water in the river, increases. We've then got your fluvial processes. So the process of erosion actually decreases, whereas the process of transportation and deposition increase. We then have also got load size, so the size of your stones and rocks decreasing, as well as velocity, the speed of your water, increasing. Now, as you travel along a river from source to mouth, you will find different river landforms in the upper, middle and lower course of your river. Each of these landforms can be referenced specifically in your GCSE specifications or your GCSE exams. So you need to know how they are formed step by step, as well as where they are located within your river drainage basin. So we're going to start by looking at V-shaped valleys and interlocking spurs, which are located in your upper course of your river. Now, the discharge in the upper course of your river, and the discharge refers to the amount of water in your river, is relatively low. This means that the river uses most of its energy to overcome friction with the river channel. The energy that it then has left over is used by hydraulic action to deepen the channel by vertical erosion or downwards facing erosion. Now, in your upper course of your river, we would tend to have the presence of resistant rock such as granite. And we have the process of freeze-thaw weathering taking place, which gradually widens the river channel, giving the valley a steep V-shape cross profile. These are the cracks that you're about to see me draw on this diagram here. So when freeze-thaw weathering happens, we get cracks in the sides of our river channel. Water will get into those cracks, freeze, expand the cracks, and then widen the river channel more and more. Over time, this weakens the rock and it breaks loose and it shifts down the valley sides. This material is then transported downstream. The winding path taken by the river is due to obstacles, such as resistant rock in its path. The river takes the easiest route over the land, and this results in land interlocking, known as interlocking spurs, which is what my final diagram is showing here. So now let's move on to our second upper course river landform, and that is known as a waterfall and a gorge. Now, when it comes to the creation of waterfalls, we have the river travelling over a band of less resistant rock after flowing over a relatively small section of resistant rock. So less resistant rock is less resistant to erosion, more easily eroded, whereas more resistant rock is harder to erode. Now that less resistant rock, like I've just said, is easier to erode, and therefore we get a lot of vertical or downwards erosion. Whereas the resistant rock is what we call undercut by the water, which is flowing over this particular area of the upper course of the river. So after a substantial period of time, this will create a waterfall. Now, the resistant rock then forms an overhang over the less resistant rock due to that undercutting taking place. And below, due to the force of hydraulic action, we have a plunge pool starting to form, which allows the waterfall to become deeper. Now, as the overhang grows, there is unfortunately not enough less resistant rock beneath it to support it and hold it up. So unfortunately, over time, it becomes weak and it cracks and it collapses into the plunge pool. This does add rocks and boulders to the plunge pool, which causes further erosion through the processes of abrasion and hydraulic action. And this further erodes the plunge pool. Now, over time, this process is repeated where the overhang falls into the plunge pool, so it makes the waterfall retreat, move back, as these processes are constantly repeated, creating a gorge either side of your waterfall. So now let's make our way further down the course of the river, and we'll now focus on some middle course river landforms. We'll start off by looking at meanders. Now, a meander is a bend in the river. Now, as water flows through the meander, it travels faster on what we call the outside bend, which creates erosion through the processes known as hydraulic action and abrasion. This can undercut the riverbank, forming a river cliff, whereas the water travels slower on the inside bend, causing deposition, that dropping off of material, to create a slip-off slope. Now, over time, the process of erosion and deposition encourage the meander bend to become more extreme, which is what you're seeing me draw now on the screen. Now, as you can see, that bend is becoming more extreme. And as this occurs, the river current will begin to erode the neck of the meander through lateral erosion. Continued erosion causes the river to cut through the neck of the meander completely, creating a shortcut for the river current. Material will then be deposited at the side of the riverbank where the former river channel current travelled through. Now, the formation of a meander then leads on to our second middle course river landform, known as an oxbow lake. And an oxbow lake begins at the stage where we left with our meander. So we've got continued erosion causing the river to cut through the neck of the meander completely, creating a shortcut for the river current. Material will then be deposited at the side of the riverbank where the former river channel current travelled through. The new channel becomes what we call more established due to deposition. So the previous channel begins to dry up. Over time, the former meander becomes completely separated from the river channel and no longer receives river water. This is what is known as an oxbow lake. Now, over time, marsh plants will then colonise this area and begin to grow, which widens the gap further, creating an oxbow lake. So now we're going to move on to our lower course river features. And the first two river landforms we're going to look at are floodplains and levees. So a floodplain is an area of low-lying land either side of the river channel, whereas a levee are what we call natural embankments formed when a river floods. Now, the river transports sediment downstream from source to mouth. Now, in your lower course of your river, it is natural for your river to flood. So when the river floods, it can transport that sediment over the floodplain, that low-lying ground either side of your river channel. Now, when a flood does occur, the river loses its energy after it bursts its banks, and it deposits the largest sediment almost immediately on the sides of the riverbank, whereas small sediment is carried further onto the floodplain, like you can see in the second diagram. If flooding continuously occurs, the deposited sediment increases, which raises the height of levees and floodplains over time. This can also increase the depth of the river channel and increase river capacity, which can then cope with a higher discharge, and flooding is less likely to occur in the future. Now, if we move on to our last lower course river landform, and that is an estuary. And an estuary is a body of water that opens to an ocean or another body of salt water like the sea. It is partially enclosed and fed by one or more rivers, but estuaries are formed when the fresh water of a river meets the salt water in a partially enclosed area. They're formed by rising sea levels, and when the water retreats when it moves back, the water volume reduces. When there is less water, the river will deposit silt, known as sand, clay, mud, to form what we call mudflats, which are an important habitat for species. So if we now take a moment to think about how human activity can affect river landscapes. And when I'm talking about human activities, I'm talking about buildings, farming, logging, industry, having a significant impact on river landscapes. So again, we're just going to bullet point a few of these down. Now, agriculture, such as farming, can influence rivers and river landscapes in a number of ways. We can over-abstract water from rivers for irrigation and watering our crops, which reduces the volume of water within the river channel. Whereas building dams and reservoirs reduces the flow of water from a river, and it changes the landscape it flows through, which in turn can affect ecosystems, flora and fauna. A dam holds back sediment, especially the heavy gravel and cobbles, and the river is then deprived of its sediment load, which it seeks to recapture by eroding further downstream. This undermines bridges and other riverbank structures and can impact on the formation of various river landscapes. Whereas channel straightening and river dredging means that the river channel may be widened or deepened to allow a more efficient flow of water or to increase the capacity. A river channel may then be straightened so that the water can travel faster along the course, reducing the risk of flooding. So if we then start to think about the causes of flooding, there are several factors that can cause rivers to flood. River flooding typically happens when there has been heavy precipitation, but we also have human and physical factors that increase the risk of rivers flooding, such as a human factor, deforestation and removing trees, which prevents interception and encourages surface runoff to take place. Impermeable surfaces and urban development encouraging the introduction of tarmac and concrete, which doesn't allow water to be absorbed into the system, will again encourage surface runoff to raise the water level in the river a lot faster, which is called discharge. Now, there are also physical factors that cause rivers to flood, and that could be heavy precipitation, saturated soil, naturally impermeable rock, and we refer to that as the geology, so rocks that naturally won't let water infiltrate, as well as the relief, so the shape of the land, encouraging steep slopes, as well as the number of tributaries that the river actually has within its drainage basin. Now, when we're thinking about flooding, as geographers, we can draw something known as a hydrograph. You might have also been taught that it's called a flood hydrograph. Either is fine. So a hydrograph is used to measure a river's flow or discharge and show the change in river discharge, the amount of water in the river, over a short period of time after a storm has occurred. And when we concern ourselves with a hydrograph, on the x-axis, we have our hours and the duration of time, and on the y-axis, we have our discharge, meters cubed per second, which we call cumex. We put our bars on there to represent our precipitation, our rainfall, and then our dark blue line represents the discharge, the amount of water in the river. So we can label the peak rainfall, the highest bar on a hydrograph, as well as the peak flow or the peak discharge concerning the line on our hydrograph. Where that discharge line rises to meet the peak discharge, we call that the rising limb. On the other side, when we then have the discharge decreasing after the flood has taken place, we call that the falling limb. Now, a river will have a base flow, its typical water level within the river. So we can also add that as a label onto a hydrograph. Now, a GCSE mathematical exam question you could be asked based on flood hydrographs is to calculate the lag time, which is the difference between the highest amount of rainfall, your peak rainfall, and your highest amount of discharge, your peak discharge. And that is the time delay it took for the water to reach the highest amount in the river. Now, hydrographs can all look different. So some hydrographs have what we call a high drainage density, where they have a high chance of experiencing a flood event and experiencing high discharge. And this I'm going to represent by showing you as a small graph on the screen now. Now, a high drainage density hydrograph will mean that the factors that have contributed to this river flooding obviously encourage rivers to flood, such as steep slopes, heavy precipitation, impermeable surfaces, and urban areas. Whereas on the other hand, we can get hydrographs which show a low drainage density, which means that a flood may have occurred, so the discharge has gone above the base flow, but not as significantly as the high drainage density one you see above. And this could be, again, because of factors that are affecting these flood hydrographs, such as gentle slopes, little to no rainfall, permeable surfaces, and deeper soil. Now, most GCSE exam specifications require students to understand the impacts and responses of flooding, but relate these to what we call case study examples. So a case study example is where you specifically investigate a location, in this case which has experienced a flood event, and you need to know some of the impacts, so what damage the flood did to that location, as well as some of the responses, how we helped. Now, quite a few GCSE examination specifications ask for you to know two examples. So we're first of all going to look at a high income country example. Now, me and my students, we study the Cumbria flood that happened as a result of Storm Desmond in 2015. And this resulted in, unfortunately, the death of 2 people, 45,000 homes being left without electricity, 8 schools being closed, 1,376 properties being flooded, bridges destroyed, and overall it caused £500 million worth of damage to Cumbria. Now, in terms of the responses and how we helped, we donated £400,000 to the area within the first 48 hours. We provided electricity generators for those homes that were left without power, and we also sent military personnel in for search and rescue and evacuation. Now again, you might have studied a different case study example here for the impacts and responses of flooding. So just have a look at what you have been taught, and if you can't find it, you can always use this Cumbria flood event as your particular location example. Now, if we then move on to looking at the low income country example, and again, you might have studied a different example, but me and my students study Bangladesh. And the reason we study Bangladesh is because Bangladesh frequently is affected by flooding due to a number of factors, such as it has a lot of low-lying land, it experiences meltwater from the Himalayas, it's had large-scale deforestation take place, and it also experiences monsoon rains. Now, in terms of damage and the impacts these flood events cause, 23.5 million people have been left homeless in Bangladesh as a result of flooding. 1,040 people died in the 2011 floods specifically, and 250,000 people are affected by diarrhoea. Now, 2.5 million farmers were also affected during these particular flood events, with 500,000 cattle being killed, so farmers lost their income. And it also closed over 400 factories. Now, in terms of the responses and how we helped and how Bangladesh helped itself, these could go into short or long-term responses. So, water purification tablets were sent to Bangladesh from various countries as a short-term response to reduce the amount of people being affected by diarrhoea. Many countries also sent millions of pounds to help provide shelters and blankets and food. 5,000 emergency shelters were also built. And in future years, Bangladesh now drains the land before the monsoon season, and it has also straightened its riverbanks. So, how can we reduce the risk of flooding? This then leads us nicely on to looking at river management strategies. So, all types of river management strategies can be placed into one of two categories. Hard engineering strategies are typically options that tend to be expensive, short-term options, and they might have a high impact on the landscape and be considered as unsustainable. And some examples of hard engineering strategies are dams and reservoirs, embankments, as well as flood relief channels and channel straightening. Now, you will need to know these in more detail, why we use them, what's their purpose, as well as the advantages and disadvantages. And unfortunately, we're not going to go through that today because this is just a summary overview of this topic. Now, our other category of river management strategies are known as soft engineering strategies. They tend to be less expensive, they typically last on a more long-term basis and are considered more sustainable because they have less impact on the environment. And these include warnings and preparation, floodplain zoning, afforestation, and river restoration. So to finish off then, my students, and maybe you do as well, need to know a case study example of a river management scheme that has been put in place in a particular region. And the example of river management that I share with my students is related to a location called Boscastle, which is a small coastal settlement in the southwest of England, in Cornwall. Now, Boscastle is surrounded by steep valley sides and is located close to a confluence where two tributaries meet. The land upstream has also been cleared of trees and vegetation. And in 2004, Boscastle experienced very heavy rain, which resulted in a flash flood. This resulted in cars being washed down the river, buildings being washed into the sea, and it put people's lives in danger, but fortunately nobody died. The village itself, though, lost a substantial amount of income due to a loss of tourism, and it had to put in a substantial amount of insurance claims. So as a result, a number of river management strategies were put in place to protect Boscastle from future flooding. So the river channel was made wider and deeper. The drainage system was improved, as well as the land being regraded and trees removed. But we also have to be mindful that river management can cause impacts on the local community. So many residents now in Boscastle don't like the new bridge that has been built, and their lives were disrupted for many years when the river management building work and construction was taking place. The flood defences that have been put in place in Boscastle will only protect against a 1 in 75-year flood event, with an overall cost of £4.5 million. So, if we now take a step back from the revision sheet, you will notice that we have now completed an entire summary of the topic rivers and flooding. I have also added a link in the description box below where you can access my example that you can see on the screen here as a PDF document. So congratulations, you have now completed an entire A3 revision summary of rivers and flooding. Thank you for watching, and I'll see you in my next video.